Hello, this is the next video in a playlist that I'm calling Applied Multivariate Analysis. And this is chapter 2 of that playlist, which I'm calling Matrix Algebra. And let's jump to today's topic, which is spectral decomposition. So we have a matrix that's square. It's symmetric, so we know that it's square. So it's called its dimensions n by n. And it can be decomposed into the matrix product of these three matrices. Now C contains the normalized eigenvectors of A, and D is a diagonal matrix with the eigenvalues as the diagonal elements. Then this product holds. These three matrices equal A. Now if we were to multiply this out, so in a previous video we looked at a diagonal times a matrix, and then these elements just were multiples of the rows. So now we're left with two vectors, and when you multiply this out, you get this. And then this can be written in summation form like this. So now notice that x here is a vector. That's an n by 1 vector. This is a 1 by n vector because it's transposed. So this is an n by n matrix. So we're summing n by n matrices to get the original matrix back. It's kind of cool how it all works out. So let's illustrate this in R. We enter a matrix into A. We store the eigenvalues into D. We store the eigenvectors of A into C. And then we take C times the diagonal matrix, D, and then C transpose, and we get our original matrix back. Even though, C is this crazy matrix. And as a reminder, diag D was the diagonal matrix with the eigenvalues. Now let's look at the spectral decomp of it, the sum part of it. So here, A1, we're going to let A1 be the first eigenvalue times the first column times the transpose of the first column. And we get this matrix, 3 by 3 matrix. Then we do it for the second eigenvalue and the second column of C, and we get this matrix. Third eigenvalue, third column, we get this matrix. And when we add them together, we get our original matrix A back. We can use the all equal function to verify it. A compared with A1 plus A2 plus A3 is true. It goes component by component and checks that. Now, for this section, functions of matrices, this first table we're not going to do much but list it and kind of note that they behave in a fashion that we think they should. So if lambda is the eigenvalue of A and x is the corresponding eigenvector, then the eigenvalues sort of behave like we think they should. So if we take C times A, then the eigenvalue of that product is C times lambda, same eigenvector. Now if we take the identity matrix and plus or minus the matrix A, then the eigenvalue associated with that result is 1 plus or minus lambda, same eigenvector. A squared, lambda is squared is the eigenvalue. A raised to the k, lambda to the k is the eigenvalue. The inverse of A has an eigenvalue of 1 over lambda. And so they kind of behave like we think they should. And while we're not going to prove it, I'd encourage you to look them up. It's a very, very simple proof, but also kind of fascinating how it works. Now this, the definition of a square root matrix, will sprinkle throughout this whole playlist. Now first I want to give you an analogy. So if we have the number 36, and this is an analogy for what we're getting ready to do, and we take the square root of it, we get 6. So then you take 6 times 6 and you get your original number 36 back. So that's what we're trying to do here. We're trying to take the square root of a matrix, and then it times itself will equal the original matrix back. And so if A is positive definite, it can be decomposed into this square root matrix, denoted by A to the 1/2, and it's going to be C. Now C are the eigenvectors of A, and D to the 1/2 is going to be a diagonal elements with the square root of the eigenvalues, and C of course is a transpose of the eigenvectors. Now this is very similar to the spectral decomp, but this diagonal elements, we're taking the square roots of the eigenvalues. Then note, if we take a to the 1/2 and a to the 1/2, so this is like saying 6 times 6 and we get 36. So a to the 1/2, a to the 1/2, we should get a back. So we plug in what we have defined the square root matrix to be. And now notice that these are orthonormal, or normalized. They're normalized eigenvectors, so that we get the identity matrix, but the identity matrix times anything is the other thing, so it can just go away. And these are two diagonal matrices. When multiplied together, get the original D back. But CDC is the spectral decomp of A, so it does equal A. Now to see this in R, we enter a matrix into A, we store the eigenvalues into D, 17, 8, and 7. We store the eigenvectors in C, and then we create this square root matrix. So it's C times the square root of this diagonal matrix, so it takes the square root of each diagonal entry, times C transpose. Now if we look at a to the 1/2 times a to the 1/2, that's the original A matrix back. And another property that we didn't prove, if we take the inverse of A, that's equal to the product of the inverses of the square root matrix. And that's true. So now the last topic that we will cover is the singular value decomposition. Now previously the spectral decomp deals with symmetric, positive definite matrices. But what if our matrix is not square? Can we still decompose it into the product of other matrices? And the answer is yes. And that's what the singular value decomposition theorem looks at. So let's assume A is n by p matrix of rank k. Then A can be decomposed into U, D, V transpose, where U is n by k, D is k by k, and V is p by k. So all this matrix product works. But what D is a diagonal matrix with values lambda 1 through lambda k. Now don't get these confused with the spectral decomp. These are different. They're called the singular values of A. And they're really the square root of the non-zero eigenvalues of A transpose A or of A transpose. These actually produce the same eigenvalues. One of them will have a higher dimension, and so the non-zero eigenvalues will be the same, and the rest will be 0 for one of these matrices. We just grab the non-zero ones, and we call them lambda squared, lambda 1 squared, lambda 2 squared, and that's really because these are the square root of these values. So we just get lambda 1, 2, 3 all the way to k. Now if we were to call these lambda 1, lambda 2, lambda k, then we would have to put the square root of lambda 1, square root of lambda 2, all the way to square root of lambda k. So but that's kind of clunky, so we just do it like this. Now U are the normalized eigenvectors of A transpose associated with these k eigenvalues. And the columns of V are the normalized eigenvectors of A transpose A associated with eigenvalues lambda 1 squared through lambda k squared. Now, since these are normalized, then this product is 1, or the identity matrix. And to see this in R, we do it this way. So we have a matrix A. Notice that it's 4 by 3. So it's not a square matrix, so it can't be symmetric. And we take the function SVD, singular value decomposition of A, and we store it in this object here. And what it produces is a list. So this is D. So these are the singular values of A. The U. So these are the eigenvectors of A transpose. And this is the eigenvectors of A transpose A. But let's store each of those in its own object. So let's store U into capital U. Create a diagonal matrix of the D. And store V into capital V. And if we look at U times D times transpose of V, we get our original matrix back. the A matrix. So it does work. Okay, well, this is all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.